go into this before we start this little tutorial exercise, let me make a very general basic point about fisheries. If you are involved and plan to be involved in fisheries in the future, that means that you're involved in policy. It's not, fisheries is not about doing research on fish. It's about doing research on fisheries, which are things that are created in nature when people and fish interact. And we would not study that if it were not for our desire to figure out how to manage fisheries. That is, if we were not interested in fisheries policy. Now, let me say something about fisheries management and what's actually true about management in general. What is management? Setting regulations, things like that, right? Well, let me put it a different way. Management is about making choices. Choices. If a fisheries manager doesn't have any choices, if the fishery is going to proceed as it will from economic dynamics and fish dynamics, with the manager being unable to intervene in any way to change the course of events, then that's not management. Okay? So a manager, fisheries management is about choices. Always, it's about choices. Now, there's something interesting about making choices. Every choice requires a prediction of the future. Can anyone tell me why I say that? Why does every choice entail a prediction about the future?
Because we want to see the outcomes of that choice?
No. A choice means that the manager can say, we're going to do A. We have a choice between doing A or B. When the manager says, I believe that policy A will work better than policy B, what is that manager doing? See, when he, in order to make his choice, he has to express a belief about what the outcome of his choice will be relative to the outcome of his other choices. So he has to make a prediction about the outcome of each choice, doesn't he? It's fundamental to making the choice, is to say, I believe A will be better. Will be better. Fair enough. So what this means is that in fisheries contexts, every management policy choice involves a model. Because as soon as a manager or his scientific advisors say, policy A will do this relative to policy B, which will do that, each of those will happen predictions necessarily has a model that justifies it. So the choice is not about doing modeling in fisheries. All fisheries choice is based on models. The only choice is what kind of model will you use to make the choice. Many fisheries choices are made by using simple trend projection models. They say, well, the fishery has been going down, and I believe it will continue to go down if I don't do something to reverse the decline. And I believe that reducing catches will reverse the decline. Well, that's using what we call just a simple trend projection model, but it is a model. So when we talk about modeling when we talk about policy in fisheries, we are always talking about modeling. And if you're involved in the future in fisheries policy in your career, you are involved in modeling, whether you learn how to do it well at all. The only choice is whether to make the models explicit. And you say, well, my God, my model could be wrong. What if I use the wrong model for my choices? Well, the answer to that is all models are wrong. None of them will predict successfully for any long period of time, right? The only thing that you need to worry about is whether you are less likely to make a bad choice if you use an explicit model than if you use your intuition to do the modeling. So an intuitive model would be that the population will keep going down. Well, that's not a good way to model population dynamics, right? And it's sure to cause you to make mistakes. And in this field of epidemiology that we're going to be talking about, this is exactly what's been going on with the people who are formulating public policy with respect to the pandemic, the COVID pandemic, is they're basically using trend projections, intuitive trend projections. It's going up, we need to reverse it, let's do something. If we don't, it'll continue to trend upward. And they're not really, in most cases, looking carefully at what trends they should be predicting, exponential or linear or so on. They're not looking at time delays, and they're making choices that are not necessarily as good as they could make if they went through and looked more carefully at the dynamics that they're trying to manage. Are you all following this? I mean, this is why I say that every student in the Fisheries Center should be absolutely required to take the ecosystem modeling courses and should be absolutely required to take fish stock assessment courses. Right? Because if you're involved in any way in fisheries policy, you're going to be involved in using the results of somebody's modeling and somebody's stock assessments and so on. You can't escape them. The only thing you can do is to get really screwed up as a fisheries policy advisor or manager in the future by not knowing what the basis is of the predictions that you're using when you make advice. Okay, that's my tirade.
Okay, I want to add a little bit, one little thing. There's one thing that really scares me, that's professional opinion, which is often an alternative to doing modeling. It's along the same line as what Carl is talking about.
Expert opinion is a bunch of people making their predictions based on whatever models they might have in their heads or down on paper. And if they're treated as equally good, whether the guy just dreamed it up out of his intuition by thinking about trends or something going on in his intuition. You know, intuition, basically, in fisheries, we're dealing with dynamic systems. And one of the things that scientists learned 4 centuries or 5 centuries ago is never trust your intuition when you're looking at a dynamical system. Your intuition does not work well to reason about what's going to happen in any dynamical system. I mean, think about basic astronomy. So you have this idea that there's a gravity source, the sun, and there's a planet out there. And the planet has a velocity, it's going in some direction, and the sun is pulling on it. How do you predict what that planet is going to do because of the pull of the sun's gravity? What's your intuitive prediction about what will happen to the planet? Well, if there's no gravity, it'll keep on going straight. Everybody understands that bit of physics. But if the gravity is pulling and turning it, most people's intuition would be that the gravity would pull it in and the planet would get eaten up by the sun. Or the planet's trajectory will be bent, and then it'll go off in a different direction, but never come back. An amazing piece of dynamical modeling was the modeling that people did to realize that what that gravity will do will cause the object to keep going around in a stable orbit. That was a really dramatic piece of modeling. Another example of how intuition has failed is one of the most famous hypotheses in ecology is what's called Chile's hypothesis. In population dynamics, Chile hypothesized that when a population of animals, he was working on mice, starts to grow, as it grows, natural selection will start to favor animals who are more aggressive about defending the resources that they're sharing with the other animals. But when they increase the amount of effort and time they put into defending their food resources, for example, that cuts into their ability to reproduce. So what Chitty argued was that a population will start to build up. Natural selection will start to favor animals that are more and more aggressive, and they will build up in the population until they, because they're not reproducing, till they cause the population to crash. And then they'll die out. And once the population gets down low enough, conditions will favor animals who reproduce rather than fighting with each other because they're not competing. So the docile animals will build back up, and then the aggressive animals will come up again. And so the basic prediction of Chitty's is that there will be a cycle out there in abundance, driven by the periodic reappearance of aggressive animals who don't reproduce. Chitty spent, and lots of other people spent their lives trying to test that hypothesis. One of the first people to ever build a model of that was a fisheries scientist whose name you should know. It was a grad student of mine named Rob Ahrens. And Rob, in a course like this, built a model of that selection process for aggressive and docile types of animals. And what do you think happens in the model when you actually do the prediction? Kind of like when you predict planets going around their orbits. Do you get cycles? No, it goes to the system goes to a balanced polymorphism, where you have a balance of aggressive and non-aggressive animals. Doesn't cycle at all. Robbie was actually the first one, and he got his master's and eventually his PhD and became a well-known fisheries scientist, because he was the first student who actually produced a real dynamic model with the real feedbacks in time that predicted correctly, that predicted a cycle, and showed that the circumstances under which a cycle should occur are actually very, very rare and very special and don't occur in most natural populations. Okay, so
No, you need to tell us one thing more, Carl.
What's that?
Ray Hilborn. Faith-based science.
Yeah, faith-based science. Yeah. I don't, yeah. Ray points out that an awful lot of people who make fisheries recommendations base their recommendations not on any real prediction, but on their faith about certain kinds of predictions. Right? That's essentially a religious argument. It's impervious to observations and facts and models and data. And he pointed out an awful lot of examples where that kind of thing does occur in, not so much in fisheries, though it does in our field, of course, but in environmental management, where people don't even think about how their prediction is going to be made. They pull their prediction off the shelf just as though they were reading it from a Bible. And they take things to be true on faith.
What scares me in this is when people know the answer, because then the research will confirm that. So my lesson from this is always to question if I'm right about something. And that also means when I run a model, what matters to me is not if I can get the model, if I get the right answer, with a model, but it is just as much to see when I have that answer, what does it take to make that answer go away, for it to break down? How can I not get these results? Under what conditions? What do I, if I change something, does that mean that that results disappears? Not just take that, oh, I got the answer that I wanted, that's showing this, but how sure can I be about it? Really questioning, is this the right way? You can do a lot with models. The models are wrong, but they are way, way better than intuition.
But let me just put it this way. If a scientist says, I have no doubt about what will happen in this fishery, and we have people right here at UBC who say things like that. I have no doubt about what the course of events will be. Then they are not scientists. A scientist who has no doubts is not a scientist at all, because it's essential to the definition of being a scientist to have doubts, to question your ability to make predictions. That scientist who's saying he has no doubts is actually doing faith-based non-science. He has complete faith in something, wherever he may have gotten it. And that kind of faith is always going to be wrong in fisheries. Well, always wrong in science. Okay, so that's enough.
Well, certainly, if there's any doubt about the outcome. I mean, if you say that, I have no doubt that if you close all the fisheries here, then the fishers will go bankrupt. I mean, that's the kind of things you can be pretty sure about.
Oh yeah, there are things you can extreme.
But when it comes down to what is the outcome of this, what do we need to do, and so on. If you know already, that's what we get into this not questioning. If you know already in your mind what is correct, and you don't question it, you are in that situation that Carl is talking about. Anyway, something much easier to deal with, Omicron.
Okay. So am I sharing my screen okay?
You are.
Okay,
The only thing when you had in the tutorial, because you didn't want to use full screen for it.
There's my grandson.
So little.
That's my son and my grandson, but that was 4 years ago. Let me get another picture up here so I can show you another one of my babies before we proceed. That one is now retired. He was a Canadian Forces fighter pilot for 20 years, and he's now retired, and he's going to do his doctorate degree in cosmology, looking at the gravity dynamics of galaxies and how galaxies form and why they have the shapes that they do. Well, let's have another one here. Oh, that's another picture, Ian. Yet another one. Oh my goodness. That's another one of my babies. The one you actually may come to know, named Will Walters, in an Ironman contest, and there's #1 son flying his fighter jet. Okay, yeah. Now, let me see.
Can you make the spreadsheet so that it's almost fills the screen?
Oh yeah. The problem I'm going to run into is
you don't need to do it full, but just drag it a bit so we can see a bit more.
Okay. All right. Now, what we're going to be using today, so we're going to build a little model of the dynamics of the Omicron outbreak in BC. What we're going to use is one of the most fundamental practical tools in modeling in every discipline in physics and chemistry and biology. Fair enough? And that's what's called the mass action principle. Just as a preliminary to this, when we build models in biology or epidemiology or anything else, there's basically two very different kinds of models that we can build. The first kind of model is called a stock flow model. In a stock flow model, what we do is to try to predict changes over time in aggregate quantities like numbers of animals or numbers of infections and things like that, or biomass in numbers. And those models involve accounting rules for gains and losses in each of the state variable values over time. The other fundamental kind of model is what's called an IBM, or an individual-based model, in which what we put in the computer is a list of individual organisms. And then over time, we simulate changes in the states of those organisms in their growth, maturation, reproduction, and death. It's the same way in epidemiology. Most epidemiology models are based on what I'm going to show you. They're stock flow models. But there are epidemiologists who build what are called what do they call it? Contact models. So what they will do is make a very large list of like all the individuals in Australia. The Australians actually did this early in COVID. And for each individual, they made a list of all the other individuals that were known contacts of that individual. And then to simulate the COVID dynamics, what they did was to look at the odds of each individual getting infected, and then each of the people he had contact with getting infected, and then each of them infecting the people they have contact with. Okay, so that kind of modeling has helped us to understand some things about why diseases don't always spread in the way that you'll see with the mass action analysis. But they're also hopelessly complex. There are individual-based ecosystem models. There's one called Osmos. And what happens in those models is basically the computational complexity becomes impossible. You can't fit the models, you can't test them, you can't evaluate them. And until we get quantum computing, you might as well just forget about them. There's way too many parameters and way too many functional relationships. Now, if you followed if you went through the tutorial before, my notes from before, or presentation from before, I encourage you to use spreadsheet models to do stock flow modeling, okay? And I encourage you to put model parameters in the first few columns of the spreadsheet, and then dynamic predictions of stocks and flows or states over time, going with rows of the spreadsheet being steps in time. And that turns out to be the easiest way to generally lay out dynamic models in spreadsheets. But in getting going today, let's talk a little bit about this thing I'm going to called this. How many of you can read what I typed here? What did I type?
Mass action.
Mass action.
Mass action principle. Okay, good. You can all read it. Is it hard to read? Okay. Here's what the mass action principle says, is that the number of events per time is equal to a constant times the concentration of actor 1 times the concentration of, well, let me change that to variable. Times the concentration of variable 2. Do any of you remember the first time you saw this? The mass action principle? You saw it in first year science. You saw it in chemistry classes where you saw a reaction rate between two chemical species that are reacting is a constant times the concentration of chemical 1 times the concentration of chemical 2. That's the rate, the reaction rate is how fast chemical 1 and chemical 2 combine, like to produce an insoluble chemical reaction product. Now, where have you seen it already in my lectures? Where have you seen this max action principle? Prey eaten per time equals a constant times vulnerable prey density times, use of times like that. That's where we do times on the computer. Predator density. Okay, so what the mass action principle says is if you want to predict the number of events or like prey eaten per time, over a short period of time, that number of events will be proportional to that's the so-called reaction rate constant or contact constant. How many prey there are to get captured and how many predators there are doing the capturing or actively searching for prey. Just having a lot of predators won't result in a lot of captures if there are no prey. Well, the number of prey eaten will be 0 if there's no vulnerable prey. It'll be 0 if there's no predators. So the way to think about the mass action principle is that it's to think of a chemical reaction vat where there's two kinds of chemicals that are floating around in the vat. And they come into contact with one another at rates proportional to how many of each kind of chemical there is in the vat. So the total number of contacts is proportional to the numbers of both of the types of things that are coming in contact. I mean, this is a central tool in modeling in areas, as I said, ranging from chemistry to biology. And it's the central tool of epidemiology, where in epidemiology, the events here are the number of new infections over a short period of time is equal to a constant, is proportional to the number of infectious individuals times the number of susceptible individuals.
Carl, can I make a question?
Yeah.
Well, coming back to the previous relation, pre-eaten per time, does the variable k tell you anything about how the system is being controlled, if it's top down or bottom up?
No, no, no. No, this is only for making a very short time prediction of
Okay,
one component of answering that question, namely how many prey will be eaten per unit time. Whether or not that results in the system exhibiting appearance of top-down behavior or whatever depends on all the other variables that are influencing vulnerable prey density and predator density. This is only predicting one component of change. Okay, remember, yeah, from the lecture you're supposed to listen to, that when we build dynamic models, the way we have to do it in order to understand how feedback effects occur. Feedback occurs when these variables change over time. The only way we know of to do cumulative longer term predictions is to make very short term predictions like this one, and then accumulate their effects over time to get the overall system response dynamics implied by them. The mass action principle is what we call a functional relationship. It's a testable proposition about how one little part of the dynamics, the number of new infections that occur each day, is related to how many people are around out there who are actively infectious, meaning with COVID, they were infected between 2 and 10 days ago. And how many people there are who haven't had COVID or are not susceptible because of previous infection, or because of vaccination. One of the big mistakes we made when Omicron appeared was to assume that the number of susceptible individuals to Omicron in places like Canada had been reduced a lot because most people are vaccinated. Because we thought that vaccination prevented infection with Omicron. Well, we should have looked more closely at the data that came out of South Africa where it was first detected. Because what those data showed was that almost all of the Omicron detections that occurred initially in South Africa were of vaccinated people, even though only about 20% of the population of South Africa had been vaccinated. So the thing that makes Omicron and has made Omicron so scary and difficult to deal with is that vaccination doesn't change this equation at all. Susceptible individuals is everybody. We're all susceptible to it, whether we've been vaccinated or not. And I'm sure you've heard this in the news, that what vaccination does is not to prevent you from getting Omicron, but prevent you from getting really sick when you get it. Okay. So now what we're going to do here is to use this mass action principle to build what's called an SIR model. In an SIR model, we're now going to be setting up a model that predicts over time. Okay. And to do this, like I showed you before, we're going to put time. Oops. I guess I can leave this cap locks on. So we're going to be predicting over dates. And what we're going to be predicting is the number of susceptible individuals. No, we're going to, let's do it this way. So the number of new infections during each day over time, our rows are going to be days of time. And we're going to predict those from the number of susceptible individuals and the number of infectious individuals. There's another kind of individual called a recovering or immune individual. Okay. These three letters, S for susceptible, I for R, leads to the name for the model that we're going to build. It's called an SIR model. Susceptible, infectious, recovering. So let's start out here. And let's put time, let's do some actual dates here. We'll start on December 1st, last fall. That's December 1st and December 2nd. Now, if you, when spreadsheets were first developed, they were developed in order to do exactly this kind of calculation where you're looking at budget items and so on over time. So right when they started building spreadsheets, they put this little trick in there that lets you say, okay, I'm going to select two occurrences of something, two successive dates. Now, can you see the little rectangular bar that I'm moving around? If you
Yes.
move that up and put it right in the corner there of that area that you selected, it changes to a fine hairline. Now I'm going to push down the mouse and I'm going to drag. And this is what's called an autofill operation. And you can see a little thing there that you probably can't read that's telling me what date it's filled in. And I'm going to drag this down and down and down and down and down. I'm going to go, let's go to July here. So 6/10 I'm at now, 22. I guess I'm going to go to the 1st of August. So I have now created a time vector. I mean a vector of dates. Okay. Now over here, I'm going to put parameters that I need in order to do the calculation. The first of these parameters I'm going to call S0. And this is the initial susceptible population. Then I'm going to have another parameter I'm going to call beta. And we'll see what that is in a minute. Okay. And beta is the number of infections per infectious individual per day when the susceptible population equals S0. All right. Now, I need to use, that's all. Oh, do. Okay, now the third thing I'm going to need is what's called the infectious period. How many days person is infectious? Let's put numbers on these things. On the initial state S0, it would be 4 million, roughly for BC. I'll just put in a number like 0.1 for beta here. And the infectious period, I'm going to make 10 days. Now, I can also put what's called derived parameters here. There's a derived parameter that you will have read about that's really important. It's called R0. R0 is the total number of infections produced per infectious person over the time that they're infectious. So how can I calculate that? Okay, beta, I've told you, is how many infections each infectious person produces per day while they're infectious. So how do I calculate the total number they produce over the whole time they're infectious?
Multiplied by the infectious period.
Yeah, that's equal to beta times infectious period. Now, what we know about an SIR model is that if R0 is 1, each individual who gets infected just replaces himself over time, and the disease won't grow. So in order to grow, this beta has to be bigger. Let's make it 0.2. Then each infectious individual infects 2 new people over the time that he's infectious, or she. Now, because I need to use these values over and over again, I'm going to name the variables. And if you watch the thing, what I do to name things is I just select the name and the number things, and I go to formulas, and I tap on a little choice called create from selection. And it will say, okay, you want to name those cells using the left column text. And I'll say, okay. So now if I look at cell B1, up here in the top left of the screen, it, instead of B1 appearing, my name S0 appears. My parameter name appears. And if I look at B2, the name beta is associated with that cell B2. So what I'm doing is that this, instead of having to, if I need days the person is infectious, instead of having to go B4 whenever I need to use that, I can just say if per. Just as a shorthand. This is really useful to name your variables when you're using spreadsheets. Otherwise, you have to refer to them by things like E6, whatever you put in that cell for whatever reason you put it in there. Okay. Now, let's go over here and build a model. The initial value for the susceptible population will be S0. So I'll type equals S0. And I don't know if you can see this, but when you type a known name, Excel puts that name in a color code. It says, I know that name. And if you look up on the left here, it highlights the cell whose name you've just used to let you know that you're using a named variable in this calculation. All right. This is not a calculation, it's just an initialization. Let's put that there. Now we need to initialize the number of infectious people that we think were around with Omicron around December 1st. We don't have any idea what that is. So I'm just going to put in 10 as a starting number. All right, now we are in a position to predict the number of new infections for the first day here. The mass action prediction is obtained as the number of new infections is beta times the number of infectious people, that's over here for that time, times the number of susceptible people, which is in column I2, divided by S0. Now, the reason I'm dividing by S0 here, the contact rate parameter K for this mass action is beta over S0. What is this ratio? Susceptible numbers over S0. Tell me an intuitive way to think about this. It's the proportion of people who are infectious. So the mass action argument is that you would get beta infections per day per times how many people are infectious. But that gets multiplied by what proportion of people are susceptible. So the lower the number of people that are susceptible, the lower is the realized number of new infections, because the lower is the number of contacts that those infectious people will have with susceptible people, as opposed to people that are dead or recovering. Now, see, I could have put this equal to K times susceptible numbers times infectious numbers. That would be the mass action equation that I showed you before. But K, I'd have to pick what K is. And K is a crazy number. Okay. Ooh, it said, I don't know what this K is that you got here. So I'll go over here and I'll say K, and I'll make K equal to beta over S0. And it's this tiny, tiny, tiny proportionality constant, and I'll name it. And it'll say, okay, I got that, I got that. Same way as doing it the way I just showed you. Okay. So we don't, and same as the chemists don't use these reaction rate coefficients because they're crazy little things. They depend on how both the things that are in contact with each other are scaled. So I just showed you a simpler way of doing it that doesn't involve that scaling. Okay. All right, so now we have a susceptible number, an infectious number, and a recovered number of 0 at this point. How do we predict first the number of susceptible people the next day on December 2nd? How does it change from December 1st if there were 2 new infections?
The susceptible people less the infected ones?
That's right. So this will be equal to the susceptible people from the day before minus how many got infected. Now we're going to ignore, because we're looking at a short period of time, we're going to ignore the fact that people move in and out of British Columbia and other things like that. Those are what we call slow processes relative to the infectious number or susceptible number. Okay. So it says, yep, left that many. How do we, now next, how do we predict the number of infectious people? Okay. Well, it's going to be equal to the number that were infectious the day before plus how many new infections occurred actually 2 days ago. But something happens now. Because we lose infectious people after 10 days. So we want to subtract off from the infectious people yesterday 1 over the inf per people. So if we had 10 people infected, we should lose 1 person out of that infectious pool. So we gained 2 new infections, but we lost 1 person who moved out. The recovered is what it was from the day before, plus how many people stopped being infectious, which is J2 over inf per people who recovered from infections. So we're having to do 2 things here. We're having to do a functional relationship to predict a critical quantity, the number of infections. And then we're doing simple accounting calculations to predict the other variables, infectious numbers and recovered numbers. You see that? And that's usually the way it is with these models. They'll have some core functional relationship, in this case, the mass action one. And then accounting balance entities that use what was there before and predicted functional relationships to move forward in time. And if you followed the examples from the video, and if you've done any of those examples yourself, we're doing very similar things, except that what we're doing there is adding births and subtracting deaths, or growing things and dying things. So there are more components of change. So an SIR model is a little bit simpler in that respect. Now for the second day, we can use the same rule as we did for the first day. Okay, now here's a really neat thing, the way they set up spreadsheets. This business of, if I move this pointer so it gets in the corner of that cell and I drag down, it will copy the formula down, but it will shift the references. So if I look at this formula, it has shifted my reference to look at the susceptible number on day 3 and infectious number on day 3. So the new infections, instead of being predicted from the initial number, are predicted from the number that are susceptible and infectious after the first day's change. So that's representing the cumulative effect of feedback. Now, can anyone tell me what I need to do next to make multiple predictions over time, prediction over multiple times with these rules that I've just put in that get me to the second time from the first? If the rules are the same, but with different numbers going into the rules each time. Do I have to retype this formula over and over again? Somebody tell me what I need to do now based on what you saw in the last tutorial, or from the tutorial.
Aren't you supposed to autofill it from the second row?
Yes. So all I do right now is I select all of my rules for change and component functional relationships that are changing over time. And I go over there and do that little fine hair thing, bingo. And my model is complete. That's all there is to it. So put in parameters, functional relationships, and one instance of the rules that you want to use for prediction over time. And then you just fill those rules in so they're used repeatedly. And they're producing different results for infectious numbers and new infections over time, because the variables that are going into the infection rate, new infection rule are changing. Now, these are hard to read, right? So what I'm going to do here, I'm going to select all these columns. And if I go to the home thing here, there's some place here I can select how many decimal points I want to show. No, it's not letting me. No, I'm just going to format the cells. There's a number with no decimal points, but with 1,000. So, okay. So it's just easier to read them. Okay. So I put commas in and things. Now, if you just look at this, you say, what the hell? You know, how do I think about this model and its predictions? Well, the best answer to that is what you see it in the newspapers every day. How can I figure out what this model actually just tried to tell me? I'm sorry.
Is that a question?
No,
Carl,
hang
that a
on.
question
It is,
about
but
after the break?
we need to take a break for just a minute. I need to help my wife get some things up from the basement. She's just been to Costco. Can we immediately take a break so I can help her?
Yeah.
Okay, 10 minutes. Be back.
Can I ask something on the meantime, Billy?
Yes, go ahead.
Just really quickly. The formula he explained on the infectious individuals on time 2.
You can leave the apples.
Could we just remember what it was really quickly? Because I'm getting something different. I'm guessing I just missed.
Oh boy. I didn't write it down. What is the infectious? I should know. I worked with Carl on this, and I should tell all of you that if it's difficult to follow, I would certainly encourage you to watch the video again. That's can be your homework, part of your homework. Because every time, even though I made models of this kind, more complex than this with Carl, it's still. So infectious.
What? No, you could, oh, bring the loose ones up. The ones that are sitting around the sink.
It's the 0.2.
If not, no worries, Billy. When he comes back, I can just ask him to put the pointer on the cell and then just verify what I got different on mine.
Yeah, let me just think. Let's put up the. 10 past 10.
Yeah. Oh, they had the real N95 masks, not the KNs. The N95, yeah. They're $1 a piece, but I figured each one we could wear.
Elena, the 10 is entered. That's just an assumption. For the next one, it is the new infections. So J3 would be new infections, so 2 minus the recovered.
Well, that's 50.
You take 10, add the 2, subtract 1, and you get the 11. You see?
Okay, thanks, Billy.
Yeah, so this is just a starting number. That's why there's no equation here. Took a little while to figure out what the equation was when there isn't any.
Great,
It's
thank
just,
you.
it can be any number. It's a low number on December 1. That's all we know. There are some issues with this recovering, and we're going to be talking about what the problem is with the way that's calculated. It's too simplified in these SIR models, but that's how they do it. But more about that later. Let's start again in 10 past.
Perfect, thank you, Billy.
Okay, so these useless ones I'm putting in here. Okay, and the KN95s that are left, I put in the drawer that has my hats and gloves in. And I've got the really good ones out on the ledge. Okay. So when you're not if you wear it and then bring it in, hang it up like on the hook behind your bedroom door or something by one ear thing so that it can air out and dry properly. No, that's not good. You need to put it somewhere where it can dry out properly.
10:10, we're back in session.
Okay. How are we doing? Can I begin? You hearing me? All right. The model columns.
Carl, just one question
Yeah.
before you start, if I may. Here on cell K3, where it says recovered 1, shouldn't we have a lag of 10 days before one person is recovered?
Yes, we should. So if you'd like, I can shift this down and refer back to just that first day. I'm leaving out the lags here
Okay,
because the lags, yeah. Once you get the basic idea set up, then it's easy to shift things down to make lags like that. Yeah,
okay. Just adjust the T0.
yeah.
Thank
I
you.
think that's actually the way Billy and I did it. We set it up the first time this way, and then we shifted things down and stuff. Now, also, these new infections aren't what we actually see when we look at the data. What we see when we look at the data is the number of people that were infected about 5 to 8 or 10 days ago. That because we don't see them until they've had time to get symptoms and get tested, right? So the cases reported are not the same thing as these new infections, which we'll look into this in a minute. But well, let's just look a little bit at these columns. The columns have functional relationships. That's the new infection prediction, a testable scientific proposal about how many new infections will occur. They've got accounting balances. Okay, that are taking things out of one pool, if you like, and putting them in other pools or making them just vanish. There's a third kind of thing we can put in here is indicators. In a column. One key indicator we look at when we're looking at an infectious disease is what's called the daily growth, or the daily little r value. Little r is what's called an instantaneous growth rate. And it's calculated by taking the logarithm of the next day's value divided by this day's value. The reason for taking the log is next value is this value times e to the r. R is the daily growth rate, so you take the log. And it says that's 9% on the first day. The reason this R value is important is that we can use it to compare to empirical data from various places to get an idea of how big beta needs to be in order to get a growth rate similar to the growth rate that we can observe in data from different places. Okay. All right, now in order to visualize what this model is predicting, what we can do is to simply plot everything over time. I can select, and you do that, the simplest way to do it is select all the columns you want to plot over time, including the column with the time variable, and then do insert and insert an XY graph where it will automatically make the X be the first column, that's time. And then it will put a plot in for each variable over time. Yeah. So, what do we have here? This is the number of susceptible people. It says they drop down really dramatically, mostly during March. But by mid-March, it had dropped by 50%. This is the number of recovered people. Notice that the disease dies out here before everybody has been infected. And that's because about out here, the R0, the effective R of the virus, drops below 1. And so the virus dies out. This is what we call herd immunity at this point. The gray line here is the number of infectious people, and it's peaking, predicted to peak in mid-March in this scenario. You can't see the new infections on this graph because they're too small compared to those other big numbers. So let's make a separate time plot of just the new infections and the daily R. Okay, so I'm going to insert another chart with the predicted number of new infections that'll be on a different scale and the daily R. And if I double click this daily R thing, I should get an option to put it on a secondary axis. Okay. So there's, in terms of the really important things, what we should, how many new infections are happening every day and how many people are still susceptible. This is last calculation's crazy because it's using 2 days data. We get the indicator. This model is saying that if Omicron invaded around the 1st of December, if it had the growth rate beta parameter that I put in here and an R0 of only 2 per day, 2, the infection should not have peaked until March, but they should have peaked at way up around 70,000 individuals being infected every day, which is really kind of scary. Imagine 70,000 people every day getting COVID in BC. If you notice that the new infection pattern is like a bell-shaped curve. This is what people early in the pandemic said the pandemic was going to look like if there was no intervention and management of the COVID. In fact, they used normal distribution bell-shaped curves in the United States to predict how many people were going to get infected with Omicron in the US. And they talked about flattening the curve by finding ways to reduce the contact rates between people, which are represented by this beta parameter. Fair enough. And that should slow it down and spread it out. So if I set beta to 0.15, if I say, if we manage how many contacts people have by restricting high contact activities like going to churches and bars and stuff, we can reduce that contact rate per infectious person per day. And that will spread the epidemic out over a longer period of time, and it won't reach such a high peak. Well, what did we see? Based on data in South Africa, Omicron's growth rate per day was over 20% per day, where we're now predicting a maximum of only 4% a day from this daily growth column. So based on that, people estimated that that the contact rate for Omicron, it's what they call infectiousness, was much higher. And that's what we see when somebody in your family gets COVID, you're going to get it, gets Omicron, you're going to get it for sure, right? Lots of contacts. This gave an R0 of 4 and a 26% growth rate. Oh, that's a little high. It wasn't quite that fast, 0.36. Oh, no, 0.33. Now, what I'm doing here is fitting the model to data in the sense that I'm looking at it, the model's prediction of the growth rate of new cases early in the Omicron growth in other places and saying, well, we'll get a similar growth rate to that in BC. Okay. So this was the first model that people did to warn about what Omicron could do in British Columbia. And that predicted a peak in cases near the end of January or the middle of January, because of uncertainty about the R value. And the prediction that was publicly issued at that time was that we could be getting as many as 200,000 Omicron cases every day in BC. Now, if you look at the South African time course, where there really was no public policy intervention to try to slow Omicron down, the case pattern in South Africa looks basically just like this, except that only a tiny proportion of cases are even reported. Now we see an apparent bug in here. Because what we have is the recovered population is going back up later on. It shouldn't go up, it should drop monotonically. So we've got some kind of little problem here. And I'll show you what it is. What we're going to find here is that we get to a point where there's so many infections each day that the predicted number of someplace down here, that the predicted number of new infections is going to go negative on us, or something is going to go negative on us. Oh, it didn't. Wait a minute. Oh, no, I'm looking at the wrong graph. Oh, okay. Sorry. This is the R value of it. The R value is staying negative. I'm sorry, everything's working all right. I thought we had sometimes when you do these discrete time adding and subtracting accounting calculations, you actually end up causing your state variables to go negative. Notice here now that with this higher infection rate, it predicts that almost everybody in BC would get infected by the end of the Omicron outbreak. Before, it was predicting about 20% still susceptible upon reaching herd immunity. Now it's saying you have to get almost everybody infected before you get herd immunity. Okay. Let's see if everybody's following at this point. And let's see if we have questions. So now we have a model that is credible in the sense that it is apparently successful at predicting the speed of the Omicron buildup and collapse in a place where there were no policy interventions, South Africa. And in India looks the same way, huge number of people infected and not being reported and stuff. But it doesn't look at anything like the data that we've seen from the developed world, where there were major interventions were made to try to stop this growth from getting so high because of the huge number of people that it would put in hospitals that would exceed hospital capacities of any system that has hospitals. South Africa, India, guess what happened? They died in the streets and they weren't reported. But fortunately, one of the characteristics of Omicron is that it doesn't kill very many people. Fair enough. Thank goodness it kills a much lower percentage of people who get it than the previous versions of COVID-19, previous variants.
Carl, would you check the chat?
Check the chat.
Last point.
Who's asking? Natalie. In terms, easier if you just interrupt me verbally so everybody knows what you're asking. In terms of the percent population required to reach herd immunity, would that have to do just with the beta or there are other factors? No, it has only to do with beta. If there's no interventions, beta is the sole determinant. It doesn't matter how I scale, how big the population is or anything else like this. Okay. And to see that, let's go back to let's go back and set beta down to do we need to say 0.2 again? So we reach herd immunity at a non-zero value. Now let me just change the susceptible population to the population of India, which is about 2 billion. Same pattern. Still coming, still ending up at about 20% of the population infected at the time when it dies out. That's exactly the same pattern as before. With a 0.2 growth rate, it's more spread out. The growth rate turning negative and the disease dying out.
It's much
Uh,
slower to
much
get
higher.
started because you're starting with infectious being 10
Yeah.
and not 10 million.
Yeah. Yeah. So go back to BC. And it really gets depressing when you look at a few of these places in the world where there were no policy interventions and no real way to manage contact rates in between people. In those parts of the world, what happened basically is that beta, the contact rate between people, is subsistence contact rate. It is contacts that people have because they have no way to avoid them. They have to go out to the public markets. They have to do this. They have to have contact with their families. They're not getting their COVID from gymnasiums and bars and things like that. They're just getting it from the activities that are fundamental, they're central to their lives. Kind of spooky situation.
So if you look at this and you find, oh, great, when we get to spring, we're going to have that herd immunity, then do remember that this is Omicron we have now, and who knows what's going to happen then. This is actually an area where Susan Allen from zoology, right from the beginning, of the pandemic has been doing a lot of interest and warning about what would happen. Omicron really illustrates that.
All right, now I'm going to put it back up to what we think actually more reasonable, 0.33, or even a bit higher growth rate. 20% is sort of what the average over the Western world's early growth rates.
Elena has a question.
Yeah, unmute yourself and ask it.
Yeah, sorry, in mine, I don't know if it makes much sense, but in this model, we are considering that the population always stays the same, right? So that it's always those 4 millions, or I can't remember. So there's no one dying, right?
We could put a population balance model in here where we add new births and subtract off deaths from the susceptible population. We could also have some of the what put in the recovered here and not put them all in there, have some of them die instead. Unfortunately, with COVID, the percentage of people that die is so small, we can neglect it. And the dynamics are so rapid. We're talking about just a few months here. I mean, look at the dates here. This is going from December to the end of January or the middle of March. The total number of new people in the population, the number of births and other deaths over that time, they pretty much balance. They're very small. And so we most of these epidemic models neglect the population dynamics of the host, is what you're talking about. More complex models, like for rabies and things like that, the host population dynamics, the addition of new susceptible individuals through reproduction, and the loss of animals to both the disease and other mortality causes is really important to make the predictions. Right, but not on this short a time scale. What happens when you need to make those predictions? Somebody tell me what I would need to do in this model if I wanted to make these time steps be like weeks or months. And so I needed to account for those other things. What can I do? Well, I can simply add spreadsheet columns to calculate things like births and deaths. Okay, I use a functional relationship for this. I predict the births to be equal to a birth rate times the number of susceptible plus recovered individuals. And they both can reproduce. They'll say, what's that birth rate? And I'll say, oh, it's just some tiny thing. And I can predict a death rate. It's a death rate times the susceptible people plus recovered. Actually, so I could then put those additions and subtractions into my susceptible population numbers or recovered numbers or both. The accounting gets a little more complex in this case because you need to do the accounting actually on all of the columns. Because people know, except infectious, I guess. They're not giving birth, but they are dying. Yeah, but certainly they're susceptible and recovered would have those longer term dynamics. But there's a more interesting thing here, and that is to ask about policy. So I'm going to insert a column in the spreadsheet. And I'm going to call it relative beta. Or just relative beta. And I'm going to set that relative beta to initially to 1. Oh, you bugger. It formatted as a date. I got to format it as a number. don't know why it wants to. And then in the new infections, I'm going to predict them each day as relative beta from the H column times the base beta that the thing exhibited. So the H2 column is going to allow me to model interventions that reduce the relative magnitude of the contact rates represented by the beta parameter. What I'm really doing here is recognizing the fact that this beta thing is not an intrinsic permanent physical quantity like a chemical reaction rate coefficient. It's the result of a whole lot of behavioral biology and disease ecology. All those things come together to produce this basic contact, this basic infection rate per infectious individual. So it can change over time for a wide variety of reasons. That relative beta can change for a lot of reasons. Okay, now in BC, in particular, something really important happened. We had we don't need that K. It doesn't- We made a major intervention on December 24th. I'll call it December 24th relative beta. And it caused the relative beta to drop. Because December 24th is when came into effect the closures of all bars and sports facilities and large meetings of people. It was the Christmas closure that said, stay home, don't visit your family. Now, let's see, put that at 0.8. Okay. Now I'm going to name it. DEC 24 beta is the name of this parameter. I'm going to go down here to December 24th, and I'm going to set the relative beta what did I call that?
DEC, DEC.
Huh?
It's called December 24.
Oh, December. One nice thing is it's keep giving me a little list of my name parameters here so I can actually remind myself of what it. So I'm going to lower the relative beta value on December 24th. Okay. Now let's look to see what happened here. Alrighty. What it says would happen with that value is that it would not have stopped the Omicron growth, but it still have peaked at 120,000 people. It just would have delayed the peak. Well, this isn't what happened. Omicron turned around much earlier. In fact, it turned around right about at the time predicted from when those interventions came in. So there must have been a larger impact of those interventions. If I make it 0.5, Still not good. Now it's still saying it would have just delayed it. 0.3, 0.35. Okay.
Carl, what's wrong with 0.5? It looked good to me.
0.5 did?
How many cases do you think we have now?
Oh, I don't know. We're not growing like that. We stopped growing on January 1st, or at the time reported cases stopped growing on January 1st. No, it had to be enough to make the case growth stop. Had to be more like 0.3. So I'm just reducing it until case growth for December 20th corresponds to us seeing it on the 1st of January.
You could set up solver to find it for you.
Okay, so now what it's saying is that the number of new cases should have abruptly dropped on January 1st and should be declining slowly. Okay. Now, what are we predicting the R value to be? That's important at this point. Because it should be a little more negative than that. We're seeing a decline of about 2% a day in the cases. No, not quite. Let's leave it at 0.3 here. So what's wrong with this model? This is basically what happened in BC, shifted over by a couple of weeks to when we observed it, to around the 1st. And the peak went a little bit higher than this. It went up to about 2,000. But it did not abruptly drop like this. What does that mean? What does that tell us? It tells us that when the intervention came online, it didn't overnight immediately cause the contact rates all over the population of BC to drop drastically like that. That actually the drop had to have been more gradual. So I'm going to try to model that by saying that instead of dropping in that 1 month, it was 0.9 times 1 times what it last was, plus 0.1 times dec beta. So what that will do is cause the implementation of the reduction to be spread out over a longer time period. It will eventually reach the 30% point, but only after considerable delay. Now we see basically what we observed. Except that now it's saying that the infection should have actually peaked a bit later than we observed. Okay. So I've got that thing going too slow. So I'm going to have another parameter in here is the beta that it started heading towards, and then the beta rate is going to be another parameter, and that's how much it changed each day. So the beta rate, I'm going to name it. And I'm going to make it about 0.2. And then I'm going to go back down here. And instead of 0.9, I'm going to go 1 minus beta rate plus beta rate. So this is a parameter I don't know, is how quickly people responded to things. So I'm going to make it something I need to look at. Okay. So now we're getting something that said if the implementation were adjusting that fast, it would have peaked sooner. Okay. Yeah, that's about right. So what this is saying is that, and what the data do show is that should have been a sharp turnaround as was observed. Should have occurred in early January, and then should have gone into a kind of flatter, slower decline pattern after that. But look what we've done to the pandemic through that intervention. We're also predicting too few cases here. And that appears to be the beta is too low. We want to get up to about 1,000 cases a day at the peak, more than that. The British estimate of R naught is 4. Now we're up to 1,500. And now we're getting up over 2,000 cases a day in early January. But that would have kept growing unless the beta rate were even lower. Now we have BC. So BC actually grew at a rate around 25%, had to have grown, and it did, of about 25% until the interventions came in. And then when those interventions took effect, we see this really severe reversal and almost dramatic peaking and reversal, with the peak occurring about the 3rd of January, which is about where we actually saw it. Okay. Now, what I'm really showing you with this is the idea that we're not looking at free dynamics out there in any ecosystem, just as we're not looking at free biology dynamics of pandemics, except in a few places like India and South Africa. So our analysis and interpretation of the data, it's just as important to model the policy changes that have altered the dynamics as it is to model the intrinsic dynamics. And you probably had a bit of trouble following my arguments about how to model those policy effects, right? And there's been a lot of debate about this. about how best to model them, like how quickly should we assume that the intervention effects came in and actually impacted the Omicron? Was it, now I've got it doing it over about an 8 or 10 day period, which seems to fit the data, but other people think it may happen faster or more slowly. And the only thing we can say is that sort of how fast things are going down tells us what this December beta was. I think more like 0.24 might give me a little better. Yeah, that's actually a little better than what we're seeing now, 2.8. Yeah, we're back down now to about half of the peak cases. So I think that's a little better estimate of the December 24th beta. So I'm not fitting to the data. I'm just using simple observations about what we saw and the relative number of cases we saw and when they, and the dynamics and when they peaked, to get a general idea of what these parameters had to have been out there so far. Now, what's going to occur in the next week?
Well, we heard that already on January 21st. But Bonnie Henry said that we are going to treat it like flu, so we're basically going to open up.
January 21st. They're out there. Well, let's just open the sucker.
Going to, they didn't do it at that time, but it's coming.
Actually, I think they're probably, let's suppose that they do just wait till March.
It's quite likely.
Let's assume they do it next week, so it happens on March 1st. We'll set that beta back to 1. I'm gonna highlight that cell range. So I think you know what's probably gonna happen here. Horrors. Right. What did I do it on February?
Well, Carl, let's stop. I think we made it here. A few comments about this. I think would be interesting. Or we could discuss a few things. One is it really demonstrates how you can build a quite realistic model, really simple, with really simple assumptions and implement it. There's a lot of details in how we fit it and so on. But you can start, one can set it up with such a simple model, and it can be in Excel, or if you're really good at it, it could be in R. And then take it from there. So when Carl developed this originally, one of the next things we did was actually to make an R version and fit that to data and so on, had a number of extra capabilities, but the starting point was this simple model. And for all new interventions, that's what Carl has been working with, has been the simple models here. Omicron model.
Well, the only way the models we're using now differ from this is exactly the point that Alberto raised, is that there's time delays in all these things. And also new infections are detected over a period of time and so on. So we do some extra accounting to keep track of the time delays, so that we'll get a little bit more realistic prediction of when we should observe things relative to when the infections actually happen. And we've looked at some more complex policy interventions. One of the things that is seen worldwide that's driving the modelers crazy is that in the Omicron wave and in other waves, there are strong indications in developed nations that the drops in relative beta, the drops in contact rates, actually preceded government interventions, dramatically so in the Delta outbreak. When Delta turned around before the government put in any new regulations in BC. So what was going on, had to have been going on, is that people in BC were watching the news and they were seeing this horrific growth rate of the Delta variant and how many people it was killing. And they were modifying their own behavior quite dramatically to reduce their risks of infection. They were staying away from crowded places. They were wearing masks. They were doing a whole lot of things. One of the things you find when you're doing these state dynamics models like this is that as long as you're sticking with modeling ecological things, where it's bad enough with some kinds of animal behavior and so on, you can pretty simply figure out what's going on. You start getting into models that involve human behavior and the complexities and subtleties of human behavior. Making any kind of actual forecast is just incredibly difficult. And so our models have just repeatedly. So 3 weeks ago, we predicted this outbreak was going to reach a peak of at least 10,000 cases per day, or reported cases per day before it started to turn around. And it got to 1/5 of what we predicted because of public policy interventions and changes in people's behavior, neither of which the disease modelers could anticipate. And who the hell, we can't model Bonnie Henry's behavior, or not Bonnie Henry, that idiot Dix, actually.
Carl, there's also, we don't know anything, we don't know that much about the real numbers.
Oh, yeah, that was the other thing that's really screwed us up with the COVID is that as the case numbers exploded here on about December 24th, the monitoring program to give us case numbers broke down. It saturated. We got what's called hyperstability in the abundance index data. In fisheries, this happens when the abundance index fails at higher population sizes to keep going up with increasing abundance of the population. It happens like this. One of the big fish problems is this happens in acoustic surveys. When you got too many fish out there, all the acoustic survey just shows us a big black blob and you don't know how many fish are in it. So we get the saturation of the observation process. And we can't tell how much went on past that. What we're doing here in BC is when we saw this violent turnaround in cases sooner than we think it should have occurred, is that what we do is assume that there was a huge increase in the number of actual cases relative to the number reported. So that the actual cases are even continuing to grow or just barely peaked just now. And then we use those actual cases to predict hospitalization data. Because the number of people that end up in hospital is now a much more stable indicator of how many infections actually had to have occurred. Thank goodness the hospitalization thing is turning around in this same basic pattern, but with a delay and with hospitalization levels that indicate that after December 24th, only about 1 out of every 6 to 1 out of every 10 infections was actually being reported. So today, out there today, there are close to 100,000 infectious people in BC. There's about 10,000 actual cases a day, or 5 to 10,000, and only 10% of those have been reported. So about 8% of the people that you might run into randomly on the street today are infectious. So that data error has made it a lot harder for people to understand the situation.
And this brings us to 11 o'clock.
Yeah.
And we should round off this class.
Okay, let's see if people have any questions just generally here. I'm going to email this this thing to Billy and he can distribute it to you.
I'll put the spreadsheet on the tutorial page in the website when I get it from Carl.
You can watch me email it to Billy.
Ah, we don't have to do that. You can stop sharing, Carl.
Huh? Let me do this before I forget. You make sure I do it. Do it right.
All right.
Stop share. Nobody wants to look at my giant fish.
What kind of fish is that?
That's
Wow.
the gentle giant. That's a fish called a black drum. It's a big cyanid that occurs in shallow water in the coast of the world, and in Florida, they're particularly abundant. And that one was 60 years old.
Big one. I thought you were in the Mekong.
No, she's a gentle giant. And they swim along really slowly along the shore and they eat oysters. That's my son over the Greenland ice cap getting refueled. Yeah.
All right.
I hated to have killed that animal. They aren't good to eat. They're just totally gentle, wonderful. If you ever wanted to love a fish, you'd want to love the black drum. They're a lovely creature.
Thank you very much, Carl. And we will continue on Tuesday talking about Ecosim. I will put more materials on the website before then. There are a couple of videos to watch again. We will be doing more practical things on Tuesday.
And I might come along and make sure he doesn't teach you anything stupid.
Oh, no.
Mm,
You're welcome.
oh,
Thank you all.
take care.
Thank
See
you. Thanks very much.
You're welcome.
Thank you, Carl.
Thank you.